In section 8.2, we start talking about how to compare two population means. So in the previous two sections and on your quiz, you would collect one sample and then you would either create a confidence interval for that sample or do a hypothesis test with that sample. And now we're going to ask, well, what if you have two samples? The first thing I want you to note is that the numbering, I got off a little bit on the numbering in my notes. The numbering, it says it's 8.1 when it's really 8.2. And so that means the homework at the end will say 8.1 in it, but it's really 8.2 homework. So just add 1 to the homework assignment. And this is going to happen again in the next video. So the next video will have 8.3 and instead of 8.2. So the numbering just got off just a little bit with the book. But I think you all are smart students. I think you're capable of figuring this out. But just change that homework assignment to say, instead of saying section 8.1, make it say section 8.2. But the numbers are all stay the same. Okay. So we're talking about two samples. Why would we want two samples? Well, if you think of most of science and most research studies that you see, they actually collect two samples of data. One of them is a control sample that they didn't do any sort of experiment on, and the other is the experimental sample. And what they want to do is they want to compare. They want to say, is there any difference between this control sample over here and this experimental sample over here? And notice this is fundamentally different from what we did in the last time when we had one sample and we compared it to some standardized number that we would have. So what we really want to do, as I said, is compare two different samples. The first thing we're going to do is talk about how to do hypothesis tests, and then we'll create and then we'll practice on 8.2, and then we'll do a confidence interval in practice, or on 8.1. So first, big apology. Big apology. I didn't give you near enough space for notes, so you might want to move somewhere else for your notes. Okay. As we look in the last section, what we saw was that when we did a hypothesis test, our hypothesis was always that mu is equal to some number, and then our alternative hypothesis is that mu is either greater than, less than, or not equal to whatever that number is. So we had some standardized number that we used. Our test statistic was given by x bar minus mu over sigma divided by square root of n. This reminds us of a z-score because we had the average and then the average for the population and then our standard deviation, which was modified by dividing by the square root of n, but that came from the central limit theorem. Then we calculated our p-value. We used the normal function on our app to make that happen. And then finally we had our conclusion, which means we either rejected h naught or failed to reject h naught. Okay, so today what we're going to do is we're going to look at what happens when we have two samples. And in fact, a lot of these things are going to stay almost the same, but they'll change just a little bit. So now instead of having just one hypothesis or just one mu equal to a number, we have two. And usually what we're going to do is if there's nothing going on in our study, it means that our two averages are actually the same. So if you did a study, say you studied the effects of winking on spreading coronavirus, you would find that the average on both sides shouldn't make a big difference. I don't think winking has any effect. So you'd expect that the average of people who wink and people who don't stay the exact same. Okay. However, our alternative hypothesis will be that either your winking either increases, decreases, or just changes the effects of coronavirus or whatever your study is. So you have two groups. You have your experimental group that does the winking and your non-group that doesn't do the winking, and you're comparing them. Okay, sorry, that was a silly thing. I'm just trying to say sometimes if it doesn't make any effect, this is what we expect to happen. If it does have an effect, then this is the result. Just as a note, sometimes we write these a little bit different. Sometimes we write this as mu1 minus mu2 is equal to 0, and that kind of makes a little bit of sense when you think about it, because if you just subtract the mu2 over here, you get it equal to 0. And this looks a bit nicer because it has a number on that side like we're used to. Similarly, we might have mu1 minus mu2 is either greater than, less than, or not equal to 0. So 0 would always be that number over there. Okay. Our test statistic changes just a little bit, but not too much. Well, actually, it changes just a little bit, but if you kind of keep everything in mind, you'll see that it makes sense the way that it changed. So instead of x bar, we're going to have two x bars. We're going to have an x1 bar and an x2 bar, and we're going to subtract them from each other. And then minus, instead of mu, we're going to have a mu1 minus a mu2. And then we're going to divide this by, this is bottom is where it starts looking really confusing, and there's kind of a real big mess, but I'm going to just write it down. It's going to be sigma 1 squared over n1 plus sigma 2 squared over n2. Now, I know this looks like a mess. If you think about it, though, this is the 2 sample version of that equation right there. And it looks a lot different, but if I were to, say, cover up one of these, you would get that it's the square root of sigma squared over square root of n, and the square root and the squared would make it just a plain sigma. So if we had only one, you notice it would be that equation. So it's maybe believable that this stays the same. Now then, once we get to this point here where we have where we find the p-values and the conclusions, so once we get to the point where we're ready to calculate the p-value and the conclusion, those stay the exact same. So once we have this z, we use the normal distribution just as we always did, and then we reject or fail to reject just as we always did. So the second half of your project looks the same. You just use a different formula for z, and your hypotheses look just a little bit different. Now the good news is this formula actually becomes a little bit simpler, because what is mu1 minus mu2? Well, this number always comes from your null hypothesis, so this number is always 0. So that means that our formula is actually a little bit prettier, and our formula is actually, this part is all 0, so we don't have to write that part down. So our formula, we can just write it like that if we like, and it'll look just a little bit better. Let me clean this up, since I accidentally erased some things that I didn't mean to. So let's clean it up. So our formula is actually x1 bar minus x2 bar divided by all of that. Okay, so that looks good, and we're ready to go. So let's try problem 8.1 and see if we can solve it. So a manager is comparing the required time to complete 2 tasks. She knows that the standard deviation of the first task is sigma equals 1.5 minutes, and for the second task is sigma 2 equals 4.8 minutes. She observes 13 employees completing the first task and records an average time of 16 minutes. She observes 7 employees completing the second task and records an average time of 21 minutes. So let's do a hypothesis test to see if there's a difference in time between the 2 tasks, and then we'll create a 90% confidence interval between these 2 tasks. So what am I going to do? I'm going to just follow this pattern just as we saw. So let me slide these over here, and we'll just start calculating the problem just as we see. So let me put 8.1 right here and start working on it. So if we're going to do our hypothesis test, we're going to write our hypotheses. Our H naught is going to be that mu1 is equal to mu2. Great. That is exactly, that's easy. That's the exact same thing. Every time you have 2 samples, you write the same thing. No problem. And now we'll have HA, and our HA comes from the problem. We have to say, do the hypothesis test that the second task takes longer. Well, what does take longer mean? Well, if we have mu1 and mu2, takes longer means that this would be a larger number. So I'm going to put my greater than or equal to like that. And now this means that when we start doing our problem, we're going to have a right-tailed test, and we're going to be solving everything in that way. Okay. Okay, so now that we have this, let's start finding our z. And so that means our z is going to be, well, we have to do a little bit of figuring out, because we figure out what is our x1, what is our x2. So we have to just figure out what is x1, x2, sigma 1, x1. Here, let me write it like this. x1, x2, sigma 1, sigma 2, and n1 and n2. And we just have to read through our problem. These problems really become, more than anything, reading problems. That is, can we just read carefully and pick out what the different things in our problem mean? So let's look closely. She knows that the standard deviation for the first task is sigma 1 equal 1.5. You were fortunate here in that number, the symbol was given to you, and so it shows up pretty clear. But you can kind of tell that it was standard deviation. It said we knew it. It didn't say this was from our sample. It's from the whole population. Okay. For the second task, the standard deviation is 4.8. Okay, so there we go. She also observes 13 employees completing the first task. So 13 is the number of employees. So that's N1. And then she says they have an average time of 16 minutes. So that 16 is the x1 time. That's x1 bar. Sorry, that's the average time it took. Now we see that she observed 7 employees. So that's that number right here. And then she records an average time of 21 minutes. So here's all of our numbers: 16, 21, 1.5, 4.8, 13, and 7. And now we just have to successfully shove that into our formula. And this is going to be 16 minus 21, and then we do divided by, and we have our square root. So divided by 1.5 squared over 13 plus 4.8 squared over 7. And now comes probably the hardest part of the problem, and that is typing all of this into your calculator. And so this really is kind of a mess to get typed in your calculator. I'm going to do it real quick, but good luck. All right, when I did it, I got negative 2.686. Hopefully that's right. As you all know from class, it is not unusual for me to mistype things in my calculator, but well, you all know I never bring my calculator, but it's not uncommon for me to miswrite or get something written down, but I think this is right. So negative 2.86 is what I got for that number. So this is our test statistic. So now we're ready to move on just a little bit. And as we move on, our next section, our next part, as we move on, our next part is to figure out that p-value and figure out what conclusion to come. So how are we going to do our p-value? Well, I'm just going to draw my picture. I'm going to put negative 2.686. You know, so whenever I write a positive number, I always kind of write it on the right-hand side. When I write a negative, I write it on the left-hand side. That's just because we know that 0 is at the center. So it kind of helps me get that picture. It doesn't really matter how you draw it, but it helps me a little bit. Okay, so that's our negative 2.686. And now I have to say, which way am I going to shade? Am I going to shade the right hand, the left hand, or both sides? And the answer is given right here. This is a less than sign. So we see this less hand side right here, so that means we're shading this less than part right over here. And so that's P. And now I just have to come to my app and see if I can figure that out. So here I'm going to grab my app, and we'll come over here and we'll come to normal. There's normal. We've got 0 and 1 already typed in. I just need my X to be negative 2.686 and hit done. And I shaded the wrong side, but the good news is the app switches it really easy. And so we shade that side right there. And so you can see my shaded side, and you can see my probability right there. Okay, so that means my probability is 0.00361. So that's what I get for my p-value. And so now all I have to do is make a conclusion. And my conclusion was to compare it to alpha equal to 0.05. So when we compare to alpha equal 0.05, we notice that p is smaller than that. So p is less than alpha. What does that mean? That means we reject H naught. What was our H naught? Our H naught was that the two averages were the same. We're going to say they're not the same. In fact, the first task takes less time than the second task. So we reject H naught. This means the first task takes less time. And you can see if you were kind of working in a business, this might be valuable. So if you tested a couple different ways of doing a task and you found that one was statistically better than the other, then you can say, okay, I want people to do the task in this way instead of this other way, and that might help you work things out. Okay, now let's come over and let's do a second problem, and the second half of this problem, and that is finding a confidence interval. But before we do that, we need to figure out what's the formula for the confidence interval. And give me just a second and we'll get to that. Okay, so what is the formula for the confidence interval going to look like? Well, here was our old formula for a confidence interval, and so you might be able to just kind of anticipate what our new formula is going to look like, because instead of having x bar, we're going to switch it for an x1 minus x2 bar, just like in that last problem, we switched our x bar for x1 bar minus x2 bar. So we'll put that in the place of this x bar. ZC will remain the same. And now the sigma, instead of having sigma over square root of n, notice if you come back over here and kind of look at what we were doing a moment ago, when, oh, sorry, we switched our x bar for x1 minus x2, and we switched our sigma over square root of n for this kind of monstrosity here. But that's what we're going to have for that square root part. So I have ZC times the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. And this is going to be less than mu1 minus mu2. And unfortunately, I ran out of space, so I'm going to have to write down a second layer here. And so we'll go is less than x1 bar minus x2 bar plus ZC times the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. One place that people often get confused is we know that we switch the minus to a plus. This minus doesn't. This minus stays the same because this comes from your sample. This is where we take the error and we add the error on and we subtract the error off. So that's the difference there. One thing of note that you might want to pay attention, or one thing of note is that your class is kind of lucky. In the past, classes have had to memorize this formula or kind of have this formula to use with. You all, since all your tests will be take home, you'll be able to just have this formula in front of you. But you might want to have it written down and handy whenever it's time to start working on your take home, so you'll know so you know where it is. Okay, so now it's time for us to create our confidence interval. So when we do our confidence interval, all I have to do is I just have to take those things that I had earlier and put them into this formula just as I see. So again, we have our x1 and our x2 and our sigma 1 and our n1 just as we saw earlier. So we have x1 bar, sigma 1, n1, and those numbers were the same. Those were the same as what we had. Unfortunately, I erased them, so I have to look them up again. And we had 1.5, 4.8. And then over here we had 13 employees for 16 minutes. And over here we had 7 employees and 21 minutes. Okay, so those are our numbers. Now there's one other number that we need in order to make this formula run. You notice we need x1, x2, sigma 1, sigma 2, n1, and n2. But we also need ZC. So ZC is the last thing we need to make this formula run. And how do we come up with ZC? Well, ZC, you'll remember, is if we were to take our confidence interval and we want a 90% confidence interval, so that means we need 90% in the middle here. How do I do this? And then this is ZC. I always use my app. And so then I come over here to this side, and instead of typing 90%, I want to type 95%. Actually, I need a decimal because it's not going to work otherwise. So I'll do 0.95 and hit enter. Why do I do 95%? And that's because it keeps going. So I need to add this 90%, but then I also need to add the extra 5% that follows in that. So I do 95%, and that gives me my ZC value, and my ZC value is 1.644. And this is a number that we've seen before this semester, so this ends up being a pretty common number that we use. Okay, so there we go. Let's now take this and try to calculate our confidence interval. And so I'm going to take all this and start putting it into my formula and see if I can get it to work. So the formula we had before is this one. So it's going to be a little bit of a mess, but you all are patient, and we can make it work. Okay, so I'll start with 16 minus 21 minus 1.644 times the square root of 1.5 squared over 13 plus 4.8 squared over 7. And this is less than mu1 minus mu2, and this is less than, and then I'll type the whole thing again, 16 minus 21, except I'll have a plus sign here instead of a minus sign here, plus 1.644 times the square root of 1.5 squared over 13 plus 4.8 squared over 7. Okay, so there are those. That's what we got for all of our results. And now it's just a matter of calculating your calculator. It's a challenging calculation. Just be patient. Just do it one piece at a time. So divide, square and divide, then write those numbers out. Just do it one piece at a time. But if you do it right, and if I did it right, then you get negative 8.062 is less than mu1 minus mu2 is less than negative 1.938. Let's make a quick observation, which is I think is interesting. And that is that there's a connection between this answer and the answer we got on the first one. So if I look at this, what this means is that I got negative 8 here and roughly negative 2, negative 1.9. So negative 1.9. And this means that there's a 90% chance that mu1 minus mu2 is in this range. Well, notice, what is the likelihood that mu1 and mu2 equals 0? Well, where's 0? 0 is over here, so notice 0 is an unlikely result. Well, what does that mean? If you did a hypothesis test, unlikely results end up rejecting H naught. So notice there's a connection between this 0 not being in our interval and rejecting H naught. So kind of notice that whenever 0 is inside of the interval, we fail to reject. And when 0 is outside of the interval, we reject. This also makes sense in the previous problems we did. If we create a confidence interval, if whatever we are testing, that null hypothesis, if the null hypothesis were inside the interval, we would fail to reject. If the null hypothesis were outside the interval, we would end up rejecting. All right, now let's flip the page over. Let's flip the page over, and we're going to do the exact same thing, except we're going to ask ourselves, what would happen if we didn't know sigma 1 and sigma 2 and had to use S's instead? And the answer is that you all are on top of this. I know that you all know what's going on. So let me just really quickly write down the things that we need to observe. Oh, okay. All right, so how do we deal with it? Well, if you remember previously, whenever we had an S, we only had to make 2 changes to the problem. Instead of Z, we used a T. Instead of a sigma, we used an S. And that was all. The whole problem stayed the same. And now, instead of using a normal distribution, we used a T distribution. And then we had to calculate the degrees of freedom. And the degrees of freedom was always n minus 1. So whatever the number was, we subtracted 1 from it. Well, okay, so now we're kind of in this. So now when I look at my new problem, what am I going to notice? Well, I'm just going to take this new formula that I had. I'm just going to take this new formula that I had and just make the same small changes. So instead of Z, I'm now going to use a T distribution. And instead of sigma 1 and sigma 2, I'm going to use S1 and S2. But the problem's going to stay almost the exact same as what we had before. And similarly, my p-value conclusion are calculated the same basic way, except I have to ask myself, what are my degrees of freedom? Well, we're going to use a very simple degrees of freedom. We're going to take the smaller of n1 or n2, the smaller of n1 and n2, and then subtract 1. And subtract 1. So we're going to do n minus 1, but we're just going to use whichever of these two numbers are smaller and do n minus 1 for that number. So that's the only difference. So we'll just have to change the degrees of freedom just a little bit, but we won't change it too much. Okay, let's try this out. Let's see if we can calculate, let's see if we can do a hypothesis test for this new problem. Oh, and I hear cats meowing in the background. I don't know if you all do. Excitement at our house. As I kind of get this set up. Excitement at our house. We have a friend who runs a pet shop, and he had some baby kittens who needed to be cared for until they're old enough to go find permanent homes. And so we have several baby kittens in our house, which my kids are loving, and they're pretty cute, but sometimes the mewing is a little tiring in the middle of the night. But okay, so let's do this 8.2 problem and make sense of it. All right, this would be a great time for you all to pause your screens. Give it a crack. I think what you'll find is it's very similar to the problem we did a second ago. The only difference is we're using T's and S's instead of Z's and sigmas. But I bet that you can work it out. Okay, so good luck. Hopefully you tried that. Hopefully it went really well. But whether it did or didn't, we can still work on the problem together. So let's write these out. What's our null hypothesis? Our null hypothesis is always that they're equal to each other. And our alternative hypothesis, this time we need to ask, well, we want to test the hypothesis that the two classes are performing differently. And so differently just means that we have a not equal to sign in there somewhere. So differently is just not equal to. So they're either performing the same or they're not performing the same. Okay, now we need to do our calculation. T, and then now I just have to look carefully at my problem and try to figure out what is everything that goes into my problem. What is my x1? What is my x2? This time I have s's, and then what is my n1 and what is my n2? So how did I know they were s's? The reason is, notice the standard deviation was the 5.5, which is that standard deviation for that first class. Notice it said that was the standard deviation for the first class. It wasn't the standard deviation for the entire population. It was just those students in that one class. Versus the second class, which had a standard deviation of 4.8 students. So as I look closely, my first class had 16 students, an average of 73, and a standard deviation of 5.5. My second class has 12 students, an average of 71, and a standard deviation of 4.8. So you can see all of our numbers ready to go into our formula, and we're ready to calculate. So let's do it. So I'm going to have 73 minus 71 on top. And on the bottom, I'll have the square root of 5.5 squared over 16. Let me erase these things. Okay. Divided by 16 plus, let's make this, I want this to be big so that we can see it, plus 4.8 squared divided by, and it looks like 12 is going to be that answer. Okay, so we do all of those. We calculate that out. It's a little bit of a pain to calculate. I got 1.024. Hopefully you did as well. So that's the number I got when I calculated this. Now, the next thing we need to do is find our p-values. And what we know is that to do our p-values, we solve the problem basically the same way as we did before, except we use our t-distribution. So we have our same picture. I'm going to have 1.024. And now I'm going to shade this side. The only difference is now I also have a negative 1.024. And my p-value is both sides because it's a not equal to sign. But which are we going to use? We're going to use the t-distribution, and we're going to need degrees of freedom. And our degrees of freedom, well, we picked the smaller of these two. We have 16 and 12. 12 is the smaller number, so we're going to use 11 for our degrees of freedom. Okay, so let me grab my app out and see if I can make it go. And so I'm going to come here to my app, and let's come back. Let's find, there's t, my degrees of freedom. I'm going to use 11. And then I want to find my x, so I'm going to use 1.024 and hit enter. So one option is I could use this greater than. One option is I could use this greater than, which is 0.16394, and just multiply that by 2. So one option for my p-value is 1.639 times 2, which is 0.327. Another option is, I think if you use this one, you actually get that number automatically. So 1.3278 or something. Okay, so there we go. So here's our number as it shows up for our problem. So P is 0.327. How is that going to compare to our problem? Well, we have alpha equal to 0.1 for this problem, and notice which one is bigger? The P is much bigger. So P is much bigger than alpha. So what does that mean? That means we fail to reject H naught. What does that mean about our tests? Well, it means we don't have evidence that there is a difference between the two tests. So no evidence. No evidence the classes are different. Okay, so that's what we got there. It could be the classes actually are different. We just haven't studied enough of them. But right now, there's no evidence they're different. And that kind of makes sense. We had 73 on one class, 71 in the other. Those are pretty similar types of scores. All right, the last task for this morning is or evening. I guess I don't know when you're watching this. The last task for you as we go through this is to do a confidence interval for that problem we just did a second ago, and that's going to be pretty similar to what we did a moment ago. So let's go back to our confidence interval formulas, and remember that our confidence interval formulas, when all we did was switch Z for T and switch sigma for S. So that's what we did in the past when we did confidence intervals. So now what do you think we're going to do? We're going to do the exact same. We're going to switch our Z with our T, and we're going to switch our sigmas with our S's. Oh, there goes those cats again. I'm sorry, I hope that's not driving you nuts. Hopefully it's pretty quiet. It seems louder to me because they're just in the other room. Maybe the microphone's not picking it up. I can hope. But okay, if it is, sorry about that. So what are we going to do? Our confidence intervals stay the same. The only difference is we switch the T's with the S's. So it's just what we did a few minutes ago. So now I just have to go through my problem, and I just have to figure out what are all of my pieces. So again, all my pieces are set up there for me to find. I've got my X1 bar, my S1, and my N1, and those are the same, and I shouldn't have erased them, but oh well. And my X2 bar, my S2, and my N2, and I just have to figure all those out. And it looks like I've got 16 students. 73 was their exam, and their average was a 5.5. And then my second group, I had 12 students. Their average was a 71, and their standard deviation was a 4.8. And then the only thing left for me to figure out is this TC value. And once I have that TC value, I'll be ready to put everything into my calculator. And so my TC value, well, how do I do that? Well, the way I do that is I come back to TC, I come back to my app, and I come back to my T distribution, and I've got my 11, and now instead over here, let's see, I'm going to want it to be less than, and I'm going to do 0.95 again, because for my TC value, I want that picture, and I want 90% in the middle, and then I need a 0.05 over here, so I need 95%. So as I look, I get 0.795 for that TC value. 5885. Let's just leave it 0.1975, maybe 6. I'm not too worried about it. Okay, so there's my TC. So what am I going to do now? Now I just have to take all of those things and try to plug them successfully into this formula that I had earlier. So good luck to us getting it all plugged in correctly, but let's see how it goes. So we plug it in, we get 73 minus 71 minus 1.795 times the square root of 5.5 squared over 16 plus 4.8 squared over 12, and this is less than mu1 minus mu2, and this is less than the same thing, so let's get rid of that and write it all out. 73 minus 71 plus 1.795 square root of 5.5 squared over 16 plus 4.8 squared over 12. All right, I feel like I'm going quickly. I hope that this is making sense. I also know there's a lot going on, so if this is difficult, count yourself as being normal, right? This is not always the simplest thing in the world to sort out. But okay, let's come and calculate these numbers out. Whenever I put all this in my calculator, I get negative 1.505. It's less than mu1 minus mu2 is less than 5.505. Okay, so I calculate all those out, and this is my confidence interval. Now, let's just really quickly think about the connection. So notice here, I now went from negative 1.505 to positive 5.505. So that would be my confidence interval, and I'm 90% confident that mu1 minus mu2 is somewhere in here. And where is 0 on this number line? Well, notice 0 is in between because you have a negative and positive. So 0 is somewhere like right here. So what does that mean about our hypothesis test? Our hypothesis test should have showed up with failing to reject because this is not an unusual result. This is a common result. And if this is a common result, then that means we're not going to be able to reject that hypothesis. And notice that's exactly what we did. When we did our hypothesis test, we failed to reject. Okay, one last note. And the last note is, if you look at the very bottom of the page, you will find Satterthwaite's formula. Satterthwaite, I think it's Satterthwaite's formula. Satterthwaite's formula. What do you notice about Satterthwaite's formula? The first thing you'll notice about Satterthwaite's formula is that it's awful. Is there an L? What if I don't, let's just say that it's very bad. So Satterthwaite's formula does not make us very happy. What Satterthwaite's formula can do, though, is it can take this T problem that we just did, and instead of using 11 for your degrees of freedom, it can make your degrees of freedom a lot higher. And what we know is that the higher your degrees of freedom, the narrower this confidence interval is gonna get. So if you wanted to make your confidence interval smaller, you could use that formula. The truth is that the difference between the formulas are very small. There's not a really big difference. For example, for this problem, if we had put all those numbers in Satterthwaite's formula, we'd have got our degrees of freedom equal to 25. And that wouldn't have changed much. It would have just moved this in by, a decimal point or something. So it wouldn't have moved it in very much at all. So we are not going to use Satterthwaite's formula this semester. And this is actually something I never do. But if you were to look up answers, say, online or use some sort of app or computer program to calculate the degrees of freedom to do the same T problem, you would get a slightly different answer. And the reason why a computer would give you a slightly different answer is the computer would use that formula because the computers, it's not hard to use complicated formulas. And then they would have a slightly different degrees of freedom. For us, I think doing it the way we did, taking the smaller of the two n values and subtracting 1 is a great approximation, and it does the problem perfectly fine for us. All right, there's a lot going on in this chapter, so you all will have to spend some time studying and working on it. Remember again, our homework is 8.2 and not 8.1, so that homework section on the bottom is worded a little bit different. One thing you'll notice, and I feel bad about this, the homework talks a lot about finding rejection regions and doing things. Don't feel like you have to do the homework the way the homework says it. I want you to do it the way that I'm doing it. And I want you to do these problems and solve these problems the way we're doing in class. If you find the homework confusing, the right thing to do is to come to the study hall hours, let me talk you through it, and hopefully it all starts to make sense. So good luck with that, and I'll see you next time where we talk about when these two differences aren't independent, but when they're dependent upon each other.